right? Did we finish the whole thing?
Up to.
Pardon?
I think we finished it, but we're not sure about a lot of stuff on it.
Well, let's kind of review some of the latter part of it. So this is the kind of important new idea, nested experiments. So there's two examples here where the data is from a nested experiment. And the idea is that in these examples, there's two factors, A and B. And we say that factor B is nested in factor A. Is the language that we use. Now the idea is that here, the spray for the trees would be factor A. We have 5 levels of factor A. And so we want to spray some trees with these different sprays and see what happens as far as whatever we're measuring. So the idea is that you can't, you have to have some trees. So the idea is you can only spray a tree with one of the sprays. You can't spray a tree with all 5 sprays. So the way this is laid out here is that there are 10 trees, labeled 1 through 10. And so these 2 trees selected at random will spray 1. These 2 trees, again, selected at random will spray 2. And so forth down the road. So we have this factor tree, which is 10 levels, but each level of tree is appearing with one and only one level of spray. So we say this is a nested kind of experiment. Or down here with the classes in the city, it's pretty similar kind of a situation. We have 5 cities, and we want to study 3rd grade students. They're going to be tested on geography, and so how do we get 3rd grade students? So we have 5 cities, and what they did here, I'm sorry, I should have made the numbers exactly the same as the numbers up here. So we have 2 classes selected from each city. So it's called school. School 1 and 2 are in city 1. School 1 and 2 cannot be in the city 2, 3, 4, or 5. Those schools are only in this one city. So school 3 and 4, so labeled, are in city 2, and so forth down the line. So we have data collected on students in each school, and so we get some replication down here on the bottom. So again, we say this is a nested kind of situation. We have 2 factors, the city and the school, and we say that school is nested in the city. That's the language that we use. And it's kind of natural, given the context, that we have to have this kind of nesting for this data to study these 2 factors. The schools have to be in some cities. It's the way around. Sprays have to be in some trees, or the other way around. The trees have to get some spray. So anyway, these are examples, pretty straightforward, I guess, of nested kind of experiments. So the issue then that comes up here on the following writing is, how do we model a nested kind of experiment? How do we analyze the data? What changes, if any, occur in our analysis? So it says here at the bottom, the observations are going to be called Y, I, J, K. I is for factor A, J is for factor B, and K is the replication. So we said we need some kind of model. Here's the model equation, sort of the standard one for a nested experiment. We have the observation is overall mean mu plus an A effect, alpha I, plus, now this is different. We would normally have, a B effect here and maybe an A-B interaction and stuff like that. We don't have that in the model here. We have this new symbol, beta J parenthesis I. And this parenthesis notation is sort of classical statistical notation that's indicating nesting. J is nested in I. J is nested in I. So in the spray tree example, the tree is B, it's nested in A, which is the I. So this is the symbol for the parameter in the model for the nested design. So there's not too many terms in the model, that's nice, but what do we have for different situations? There's case 1, 2, and 3 listed here, which are sort of familiar to you now. Both factors fixed, both factors random, one factor fixed, the other random, mixed model. So we have these kind of circumstances for the terms in the model. We have sums of squares in the usual way, and we have a new one that comes up right here. Sum of squares B parenthesis A. And here's its formula. Well, looking at the formula doesn't really tell you a whole lot. You can say something about it, you can say what it means and so forth, but I don't think that's especially helpful. This is the definition of sum of squares B within A. And here's some parameters, phi of A and phi of B, in the case those are fixed factors. So then we have the idea of, okay, we're going to have sums of squares calculated, and then we're going to put these in an ANOVA table. So we have to know how to form F tests for this ANOVA table. And this layout tells us how to do it. So if we have the fixed model, here's the expected mean squares, and so things are easy. The A is tested with this one, and B is tested with this one, straightforward. We come to the random case, and so we would say B is tested with this one, A is tested with this one for the denominator, right? So there's a change in the random model. And then we come here and look at the mixed model, where A is fixed, B is random, and these are the expected mean squares. And so again, you can see what are the proper F tests. This one has this for the denominator. This one has this for the denominator. So things are matching up nice, and the natural denominators for each of the two tests that we might want to run, depending on which of the three situations we're in. Okay, so that pretty much says what we're going to do here now. Then on page 3, there's some stuff here for the case of fixed effects model. So it just said, these are some things that we've done before in earlier models. Here's the model equation. Suppose these are both fixed effects. So y bar ij dot says take this and average it over k. So that remains. That has no k, and that remains. That has no k, and that remains. And we would just get the average of these out of k, which we could write with that notation. Then we ask, what's the distribution of this kind of thing? Well, these first three pieces are just constants. And so they pull out here in the mean of the normal distribution. And the variance is going to come from the random part, which is this E bar thing here. And that has a variance simply spread over n. N being the number of terms in this average. So that's kind of easy to do, straightforward. We talk about the distribution of y bar ij dot. Go one step further and go y bar I dot dot. So that says, start with your basic observations and average over j and average over k both. And this is what you're left with here. Now, when you average over j, the sum of those is 0 by our model assumptions, right? So when I add these over j, the beta j's add up to 0. So that drops out. So that's why it's not in here. So we have the mu retained, the alpha I retained, the beta j has summed to 0, so that's gone. And then we get the average of the e's, which I write that way. And so now we can state what's the distribution of this thing fairly easily. It's normal. Here's the constant mean. And then the variance is from the E bar, which is again sigma squared over a sample size, which here is NP. Now, the next two lines just take differences of those two things, and those are fairly straightforward to look at as well. So if we want to talk about the difference of two of these, where we have a different j and j prime. So the difference between two of these things is again normal. Write down the pieces, looks like this, state what the distribution is. This constant becomes the mean carried over there. And the variance comes from these two random pieces. It will be the sum of the two variances, and they're the same number, so we get 2 sigma squared over n. We're doing the same thing in the last line here, with the y bar I dot dot, y bar I prime dot dot. We get a similar kind of line here. So these would be distributional results that we would use if we wanted to do, for example, pairwise comparisons. We wanted to compare alpha I with alpha I prime, so this would be our estimate, and we could build a confidence interval. We could do t-test type things with these differences and so forth. So that's the point of these lines anyway, to give us some stuff to work with if we wanted to build some, say, confidence intervals. Here's a machine example. There's 4 machines, and they can be run by any number of operators in the plant. And so what we have is 3 operators are going to run machine 1, 3 operators are going to run machine 2, 3 are going to run machine 3, and 3 are going to run machine 4. The catch here is that these aren't the same operators, even though I've called them operator 1, 2, 3, operator 1, 2, 3. They're different operators. There's 12 operators in this experiment. Factors. One is the machine, the other is the operator. Both of them might affect the response. How do we get data on these 2 factors, and how do we analyze the data is the issue. So anyway, what we have here is a nested setup because the operators are working on only one machine. This could have been organized a different way. We could have selected 3 operators from the workforce, and then these 3 operators could have used machine 1, then they could have used machine 2, then they could have used machine 3, 4, and 5, and so we wouldn't have a nested situation there because the same operators are being reused again in the subsequent experiments. But that's not what was done here. So this was set up in a nested fashion. How do we analyze this data? I apologize again for this kind of messy Minitab approach here. What I did basically was appropriate. I typed in these numbers in 12 columns in Minitab. So there they are. I did all the work of typing them in. Now I've got to get those arranged in a single column, right? So I should go back and start all over again. But I said, I'm not going to go and start all over again. I'm going to use what I've already done. And so that's what all this fussing around in here is going on. So I'm not sure how familiar you are with various Minitab commands, but Minitab has matrix commands, for example. So you can take a set of columns, like these 12 columns, for example, and you could make that a matrix. So that's this first command. Copy C1 through C12 and store it in a matrix called M1. M1 isn't visible to you. It's under the table, so to speak, but it's there. So M1 is the matrix of these numbers. Now what I want to do is to take that matrix and transpose it. So that's the next one. Transpose M1 and store the answer in M2. So M2 is these numbers, but transposed so that the first row is the first column and the second row is the second column. So now I have this matrix M2, which has two columns in there, and I want to get one column out of this. So I keep going. I say copy M2 into new columns, C13 and C14. So this first row is the contents of C13, and the second row is the contents of C14. Now that I've got these two columns here, what I can do in Minitab is stack one column on top of the other with the stack command. So I'm plowing away, stack C13 on top of C14, and store the answer in C15. So now, finally, in C15, I have the original data arranged in one column. It would have been shorter for me just to type in the numbers all over from scratch, but I chose to do it this way. Sorry about that. So now I have C15 has those numbers in a single column, length 24. Now I have to set up some columns for the values of the machine factor and for the operator factor. And so that's what I'm doing here with these set commands. Set C16, 8 parentheses 1, 2, 3. I think the syntax goes, I'm going to set some numbers in C16. The numbers are going to be 1, 2, 3, and I want them to repeat it in a certain pattern. So I put 8 parentheses 1, 2, 3. Now I think what that's going to do is to put 1, 2, 3, followed by 1, 2, 3, followed by 1, 2, 3, and keep doing that 8 times. So this gets a 1, 2, 3, and these get a 1, 2, 3, 1, 2, 3, 1, 2, 3, etc. down the line. And so that's how I, without typing the numbers out, that's how I get that column set up for the value of for the values of the operator. Now I want to do the same kind of thing for the machine. And so that's the next set, set 17, 1, 2, 3, 4, put that in parentheses, and put a 3 on the right side. And that's going to do 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. It's going to repeat in the other possible way. So it matters whether I put the digit in the front of the parenthesis or at the end of the parentheses. And then I wanted to do that twice. So I put 2 of them on that line. And so now I've got the data is in C15. C16 contains the operator number, and C17 contains the machine number. Now, what I should do is to name these columns. It's kind of hard to remember as I go on what's in what column, where I just have numbers for columns. So I partially labeled some things. And so you see if I do a GLM of Y, so I must have labeled the data columns 15 as Y, GLM Y, and then the model is machine, and then C16 parentheses C17. Notice how we do the nesting indication to Minitab in this kind of syntax here. So anyway, sorry that's a little confusing. You have to read that slowly and carefully to figure out what I'm trying to do there. So basically, it's a GLM command in Minitab. There's the model equation. Operator is random. And I asked it to do a bunch of things here that it didn't do. So Minitab nicely gives us an ANOVA table. We can find the F-tests and do the testing simply there. It gives us the expected mean squares in this tableau here. And so we can see what the proper denominators are, although it did the right ones up here in the ANOVA table as well. And it gives us some other information which we may or may not be interested in. So anyway, my point here is that for a nested problem, Minitab handles it in an easy way. Basically, I just used the syntax GLM y equals a space b parenthesis a. If you're typing a line, that's what you type. And A and B are the names of the factors that you're talking about. Now, when I'm using Minitab, I'm often just using the menu, so I have to just check things in the menu to indicate this is the model. So I can do that in the menu as well. So that's just one example, but it's a very basic example that shows you that there's nothing scary about a nested model. Two factors, one nested in the other. How do I get an analysis of variance table and do F-tests? That's it. Very straightforward to get that set up if you're using Minitab. So then at the bottom of page 4, it takes up the messy case, unbalanced two-factor nested models. So this is always hard. Unbalanced data is almost always hard in statistical analyses. So I'm going to write up some things about the unbalanced case. So how can we get unbalanced? Well, let's see, this starts here. I goes 1 to little a for factor A. J goes 1 to bi for factor B within the ith level of A. So what you have to be envisioning there is something like, you might have A equals 1, A equals 2, A equals 3, and here you have B1, B2, and you have B1, B2, B3, B4, there are 4 B's when A is 2. And maybe you have something like B1, B2, B3 when A is 3. So the point is that in the notation, it's indicating that we can have different numbers of B's in the differing values of A. Okay, so this is where it started to become unbalanced. Now, as far as the replication in these things, it says K goes 1 to Nij. So K is the replication subscript. It's how many observations do we have there? How many observations do we have there? How many observations do we have in each of these junctions here? And so forth. The data, we have different number of replications in the locations. So that's all specified in the notation above. It says let Nij be the number of observations for the ith level of factor J. So Ni dot. Now that differs in each value for A, so we have a symbol for it, Ni dot. M is the sum of the BJ's on J. It's the number of observations for B. So looking at my little picture here, the number of observations for B seems to be 2, 3, 4, 5, 6, 7, 8, 9. And my notation here isn't really very good because here BJ means something, but in here BJ means something else. Right? So those tangled up in what you're writing there in these notes. Anyway, so now you can see how the data can be very unbalanced in several ways. Different numbers of B's within each A, and then different number of replications in each of the cases. So if we have these unbalanced kind of data sets, what's the model? Well, the model equation is exactly the same model equation we had before. Nothing needs to change there. But then we have the three cases. Both factors fixed, both factors random, mixed case, one factor fixed, the other is random. So those are the standard assumptions in those three models. And so we continue along, we say, well, we define means the same as before, sums of squares the same as before, and notice here's our new one, sum of squares B within A, and it's right in the list. So we use the same formula that we had before. And then here's some constants in the case of fixed factors, as is typical. So now we define some new things. We define A1 to be this messy sum, A2 to be this messy sum, and B1 to be that messy sum. And they're going to be used on the next item here. When we ask ourselves, how are we going to do F testing when we have unbalanced nested data? This is the table that's going to tell you what to do. So it's going to say you have these usual sums of squares. Calculate them by the usual formulas. You have, for the fixed model, these expected mean squares, and you can see the error mean square is going to be the natural denominator for both of the other tests. You go to the random model, both factors random, and now something messed up. When we had balanced data, this constant was the same as that constant, so we had a natural denominator for this one here. Now it's different. So this is not the same as that. So you don't have a natural denominator for testing A. You do have a natural denominator for testing B. Here it is. You use as a denominator for this one. And then the same kind of thing happens over there in the mixed model. We have a natural denominator for this one, namely the error. We don't have a natural denominator for A. This one doesn't work. It's not the only constant that works. So So what the handout goes on to do on this page is to say, well, we've talked about this kind of issue before, and we said one possible solution is the pseudo-F test idea. So basically what I'm looking at is, let's see, I'm going to look at the mixed model. So I'm looking at the third column over here. So I want to construct a mean square whose expectation is right there. So I look at what I have available, and I I only have B within A and here to work with. So I say, let's try a linear combination of those two. So theta, mean square B within A, 1 minus theta, mean square error. Now, set up the parameter theta so that this is equal to what I want. I want to have a mean square whose expectation is this, so I can use it as a proper denominator. So it's a simple thing to do. Just write down the equation, and it's high school algebra to solve, and you get what I've claimed here. Theta should be the ratio of those two constants. So in order to know what theta to use, you have to calculate these two constants, right? So that can't be skipped. So there it is. And then this mean square with that theta in it has some estimated degrees of freedom by the Satterthwaite formula again. This is the estimated degrees of freedom formula. So we have to plug in some numbers to work that all out. And so now we finally have an F-test, a pseudo F-test for testing A. So that's kind of a messy solution to the problem anyway, but that's what happens to us when we have unbalanced data. So here's a small example. Here's factor A at 2 levels, factor B has 2 levels there and 3 levels here. And then the replication within each of these 5 cases is given by what you see here in front of your eye. So what I noticed in Minitab is that in the menu for ANOVA, there's one choice that says nested. That's a good choice, let's try that out. So in the menu, I chose that one, and here's my data, you can see it's there. And then when I use the menu, Minitab said this is the command that I'm using. And I didn't like that already because it's not indicating which factor is nested in which other factor. Yes?
It depends on how you write it. If you write A, then B. B is nested in A. But if you switch it around, it's the other way.
Yeah, it must be some convention like that. I didn't check which way it went when I did this.
I did just on this last one.
So well, I'm not sure which way I built it in the menu. I don't remember even what the menu looked like now. But anyway, it gave me this output here. And so you can see I'm trying to calculate A1, A2, B1 here, and I got those numbers, and they're matching up what I'm seeing in the expected mean square here, which is good. And so now I'm going to build the pseudo F-test, which does not appear in the table up here, right? It's missing. So I'm trying to build that pseudo F-test here, and then I kind of just quit. I said, there's a better way to do this. And so I said, let's go back with the same data and use the GLM command because I know how that one works. We used it in the balance data set that we had prior to this one. So let's try GLM y equals A and then B parenthesis A to indicate B is nested within A. B is random. Expected mean squares are called for. So I get this analysis of variance table, and now it's complete. It has F tests in it, right? Which is good. The test on A has a little X on it, and it says this is not an exact F test. I know why. So here's the expected mean squares, and you see the numbers 2.6866, 3.0 right in there. And those are matching. Let's see, I've said here B is random, so I guess we're in this case over here. So you're seeing A1 and B1 in that Minitab output. So there's A1, there's B1, I've written them over here on the side, and the ratio is 0.8955. Then Minitab went on and gave this last layout here, which says the error terms for the test. For A, it's going to use a synthesis of error mean square, and it's this right here. Well, here's our theta, mean square B within A, plus 1 minus theta, mean square error. So this is our cobbled together mean square right there. Here, this is my writing correct, because I think I checked the arithmetic on this to see that A1 and B1 really do come out to be these numbers coming from Minitab. So anyway, this I'm confident in. So if I'm recommending anything to you on how to analyze unbalanced nested data, I'd say this is going to do it. Minitab seems to handle it quite well and do the right things, and that's exactly what we need. All right. More nested experiments. Yes, I should have mentioned this. Our textbook has a chapter on nested designs, chapter 26. So you can find chapter 26 there and read more about this. Perhaps explained in a different way. There's some examples there and so forth. So chapter 26 is good for this topic. Now what I have here in this handout is some examples that I took from other sources. And so if we start on the beginning here, you see first of all a set of data. And it has machine A, B, C, D, E. So apparently there's 5 different machines. And then there's head, 1, 2, 3, 4, 5, 6, up to 20. So there must be 4 heads in each machine that can be used. And then in each of those machine head combinations, we've apparently got 4 observations that you see in these columns down here below. So here's a data set where we have 2 factors, machine and head. And the head is nested inside machine. I don't know what these machines actually look like, but typically a machine might have several positions on it where grinding can take place, or fitting can take place, or some action can take place anyway. And these machines apparently have 4 heads. And now the results that they get from a given machine, they're going to make 4 at a time, right? They're not going to be uniform. There's going to be differences. And they might want to know whether there's any influence of the heads, for example. The head on the right, the head on the left, fore or aft, whatever. So anyway, they have this kind of data set up, which is in a nested design. time to talk about this today, but this is an interesting little tableau here. You remember that page that I gave you on how to calculate expected mean squares? Weeks ago now, we haven't really emphasized it in class at all. This is a good little exercise to check that out. And there's only 3 lines, so it's not very long to do this. So figure out if we have a term in the model for machine, a term in the model for head nested in machine, and then an error term in the model, just 3 terms in the model. How do you figure out the expected mean squares? And the way this is laid out, I, which is the machine, is fixed. J, which is the head, is random. That's what the R means there. And K, the replication, is also random. So anyway, this is set up, and once these numbers are determined, from these, you can write down the expected mean squares. And when you look at these expected mean squares, you can see the obvious thing. Test about B, use the error. Test about A, use B nested within A, use this one. So that's all really apparent by looking at these expected mean squares. So, turning the page, we see here the Minitab output for this nested experiment. And it's very straightforward to look at this analysis of variance table, even as far as the p-values over here, and say head nested in machine at the 5% level, not significant. Machine, not significant either. So neither factor is significant on these F tests. Simple to do, just looking at the ANOVA table. The trick is that Minitab does this table correctly for us. Okay. Apparently, rotary Minitab on this asks for expected mean squares, and so we've got this array out here, and these entries right here match the table on the previous page with the right coefficients. 4, 4, 16. So nicely that matches up to the handwork for expected mean squares as well. All right, so that's enough on this example. A very short, simple example. Let's look at the next page where a new example is taken up. And this one's got a little bit more fanciness to it. Let's look at the data down at the bottom of the page, first of all. So what you see here is we have 3 groups of, these are soldiers actually. Group 1, Group 2, Group 3. And then teams of soldiers are formed. So for Group 1, we have 3 teams. For Group 2, we have 3 teams. And for Group 3, we have 3 teams. I forget what the groups were here. They were related to experience or something like that. I think it's on the page before this one, which I don't have here to look at, so I can't say exactly what that is. So anyway, let's look at this area one more time. Suppose there's 3 groups of soldiers, maybe by years of experience. Group 1 is the new recruits, no experience whatsoever. Group 2 has a little bit of experience. Group 3 are seasoned veterans with a lot of experience. So from those soldiers, we form teams. We form 3 teams from these guys, 3 teams from those guys, 3 teams from those guys. So we've got these 9 teams laid out here. And naturally, the teams are nested within the groups. Okay. So this example is more complicated because there's another factor in it over here. The way that they're doing this work of loading the rifle, loading the gun, whatever it is, can be done by one of two different methods. So they can use method 1, they can use method 2. So each of the teams does 2 replications for both methods. And so we get data that looks like this. Now, this is much more complicated than what we had a moment ago. We've got team surely nested within group. What about this factor over here? Is it nested in anything? I don't see it. I don't think so. So this is like a complicated effort in this example, in this data, to have this factor method set over here as well. Well, how are we going to deal with this? Well, let's go back and look at the beginning, where this reference writes down a model. And this is very important to write this down to say what we believe is going on. So we have Y, I, J, K, M. I is for group. J is for team. K is for method. And then M is the replication that's left over. So we have an overall mean view. We have MI for method I. Whoops. Now, he's tricked me up. He's going to call this subscript I over here, method I. So we have method I, G, J would be group J. Okay. So we have a group effect occurring in here. Now we allow an interaction between M and G. Okay. Now that's a fairly straightforward kind of thing from what we've done in earlier places, because this factor method over here is crossed with group. And so we can have main effects for group, main effect for method, and we can have an interaction between these two factors as well. No nesting going on there yet, just simply crossed factors. So we're specifying that by this term in the model, MGIJ. So now we bring in the nesting idea, and there's this term here, TK nested in J. K is the team, and J is the group. So here we're saying team is nested in group K parenthesis J. Team is nested in group. Now this one here is the puzzlement to me. MTIK nested in J. So apparently there, with this term, we're saying I and K are nested in J. Let's see, this is J. This is I. So what this term is saying, I have to slide this around so much, is that I and K are nested in J. J is the group up on top here. So we're saying I and K, the other two variables are nested in J. Now that's kind of a tricky thought to imagine what's going on there, but that's the interpretation I can say for the meaning of that term in the line. MT, IK, parenthesis J, IK, that's the J. I is over here, K is the T. Those two in combination are nested in the group. Kind of a sophisticated idea as far as what's going on. So anyway, the statistician, the researcher is free to specify any kind of model they like, and this is the one that's specified here. Now what we have is that if we have those terms in the model, we use our method I don't have time to do this here today, but you can check this out by our earlier handout about how do you calculate expected mean squares. Here's the method of setting up these columns. Once you have these columns set up, you do various multiplications, and you come up with this label for the column for expected mean squares. So the point is, there is a way to determine expected mean squares by hand work. You don't have to let the computer do this for you. You can do this by hand. J is fixed. No, that's an I. I is fixed. J is fixed. K is random. And the application M is random as well. So this is kind of a mixed model that we wrote up there. I and J are fixed, and K is random. And those specifications about what the factors are like, are they fixed or random, are used in setting up these numbers. And so they're going to be, that information is then going to be used in generating these expected mean squares over here as well. If you change around and you say, oh no, factor K was fixed, well, that changes some things in this column, that changes some of the products, and it'll change something over here as well. So this is a kind of touchy business anyway, as far as how this all gets calculated and fit together. The nice thing you can rely upon is that there's an algorithm for getting the answer. That's what a computer program can be good at. So Minitab can be using, hopefully, the right algorithm to calculate these kind of things. So then on the last page, turning it over, we have this Minitab output again. And you see it's complete. What else would we want? Here's the ANOVA table. Here's the F statistic. There's the p-values. You can see that one's significant and that one's significant by a huge margin. It's a massive F statistic. So 2 are significant and 3 are not. So that's all very quick to read looking at the ANOVA table. So that's not a big deal. You know how to do that. You know how to look at that ANOVA table, interpret the results. Here's a tableau laid out here about the expected mean squares, and these are the information about expected mean squares. And if you check, flipping the page over, these will agree with the expected mean squares on the previous page. So Minitab did it right. All right. And that's basically it. So this last paragraph here is still got some useful thoughts in it as well. It's saying, when you look at this ANOVA table, you look at this p-value of 0.04, which was for team nested in a group. So you're going to say there's some differences between these teams. So now your next step would be to try to explore what's the difference in the teams as they're nested within groups. And so that's what they're taking up down here. They're saying the well, as you see here, they're going to talk about some kind of multiple comparison procedure, and they're going to use what they're calling here the studentized range method. We haven't emphasized studentized range method in this class, so don't worry about that at all, just ignore that. But you can choose various things here. The idea is I want to compare these teams. What's different about them? So I could do some kind of multiple comparison method based on Bonferroni. I could do some multiple comparison based on Tutti, pairwise, okay? And we could do Chaffee as well, but that wouldn't normally be done here in a problem like this. So anyway, we can choose our favorite multiple comparison procedure and figure out how to make some statements about team differences. This little graph at the bottom of the page summarizes the result. It's fairly self-explanatory to read this. Teams 1 and 3 are pretty much equal, but team 2 is wildly different from teams 1 and 2. Okay, so another example from another source with some nice Minitab output to illustrate the calculations. Now, I don't think I have it on some paper here. No, it's in my other folder. So let me draw out yet another example here for you. If I have two factors, A and B, and B is nested within A. Let me write this kind of notation. B is nested within A. So we might envision some of the data that we've looked at here today. A could be 1, 2, 3, and B could be 1, 2, 3, A could be up to 4, say. 1, 2, 3, 1, 2, 3, 1, 2, 3. So we had an example like this earlier in our paperwork here. And then we have data under each of these circumstances. Like that. Now what I want to do here basically is to open up the idea that factor A may be defined from two factors. Factor A, what I'm calling factor A here, might be defined from two factors. So let's suppose that factor A, what should I write here? Take this layout that I have here and I twist it around, I could put A on the rows, A equals 1, 2, 3, 4. And then I could put B on the top, 1, 2, 3. And then there would be some data in each of these cells. This is the way I wanted to write it. So let me switch it around so that A is the row, is in the row position. Okay. Now, what I wanted to do is to say, suppose A is not one factor, but it's defined from 2 factors. So for example, maybe we have, let me not call it A, let me call it C1, D1, C1, D2, C2, D1, C2, D2. So there's 2 other factors that I'm calling C and D, and now this is A1, this is A2, this is A3, this is A4. And then the rest of the data layout carries over from above. What I'm trying to express to you is a simple thought, really, to say, if we know how to talk about 2 factors, A and B, where B is nested in A, we have a picture like this in our mind, okay? But what if factor A wasn't just 1 factor, but what if it was 2 factors? Like this. I have 2 factors, C and B, and they each have 2 levels, and one I've written here. And I'm artificially calling that combination A1, that combination A2, A3, and A4. So that's just artificial labeling things. So what I can say is that I can do analysis of this data where I have 2 factors, C and D, and B is nested in both of them. Factor B up there, B was nested in A. So down here, B has to be nested in both of them. Okay. So I don't have a number example for this kind of situation, but the context should be clear enough for you to think about as a way to extend further the idea of nesting.